In the last recording, we found out that coset multiplication is not always well defined. And in this recording, what I want to do is I want to work on fixing the problem with coset multiplication that we discovered in the last video. So we're going to let R be a ring, and S is going to be a subring of R. Now we already know that the operation defined as A plus S times B plus S being defined to be AB plus S, this operation is not well defined on the set of cosets, on R mod S in general. And that's the problem that we're trying to fix. So our question for this video is, can we find some kind of conditions on the subring S that ensure that our coset multiplication is in fact well defined on R mod S. Now, in order to investigate that, what we're going to have to do is we're going to have to look at two cosets that have two different names each and multiply them together. In other words, what we're going to do is we're going to start off by assuming that A1 plus S is equal to A2 plus S, and we're also going to assume that B1 plus S is equal to B2 plus S. Now that top one says A1 minus A2 is equal to something in S, and I'm just going to call that something S1. And the fact that B1 plus S is equal to B2 plus S says that B1 minus B2 has to be inside S, and we'll just let that be S2 for some S2 inside S. Now, what we want is we want A1 times B1 plus S to be ensured to be the same left coset as A2 B2 plus S. If we can get this ensured, then we will have coset multiplication is well defined. In other words, it's important to realize that if this is true, then our coset multiplication is indeed well defined. So that's why we want this. Well, I happen to know that that will be true if and only if A1 B1 minus A2 B2 belongs to S. And so our starting point is that we're going to be looking at this particular idea, and we're going to be seeing what can we do that will ensure that this difference here, that A1 minus B1, or A1 times B1 minus A2 times B2 really will belong to S. So let's actually explore that. If I just start off with A1 times B1 minus A2 times B2, I can do a bunch of things with that, and the first thing that I'm going to do is add and subtract something. Well, technically I'm going to subtract and add something, and the goal here is to do some partial factoring. So I'm going to have A1 B1, and then I'm going to subtract off A1 B2. But if I'm going to subtract that off, I have to add it right back so that I don't change anything. And then, of course, I've got the minus A2 B2 at the end of this. Now, this is an equation in the ring R. And the stuff in red is just the 0 in R, so we haven't changed anything. Well, what I want to do now is I want to realize that I can also put parentheses in, because addition is associative inside all rings, and when I do that, I can use the distributive law. On these first two terms, I can factor out an A1 out of the front, leaving me a B1 minus B2 inside the parentheses. And on the second one, I have to factor the B2 out at the back end. So I get A1 minus A2 times B2. And this is by the distributive law. So this step is by the distributive laws inside ring R. And what I want to notice is we have now things that we recognize. I want to go back up and point them out. A1 minus A2 is just is S1, and B1 minus B2 is S2. So I'm going to substitute those two facts in, and when I do, what we get is A1 times S2 plus S1 times B2. And we want to ensure that A1 times S2 plus S1 times B2 is inside the subring S, and we want that done for all choices of A1 and B2 inside the ring R, and all choices of S1 and S2, and I have a copying, no, I have a copy, don't have a copying mistake, it's okay. S1 and S2 inside our subring. And this looks very familiar. I want to recall that if S is an ideal in R, then I will know that for any A1 or B2 inside R and any S1 and S2 inside S, that we will indeed have the products that we need belonging to S. We will have A1 times S2 belongs to S, and we will have S1 times B2 belongs to S. That's the definition of ideal. And so what I notice is this. If S is an ideal, then I know that the thing that we are stuck with here, well, let me start it off with A1 B1 minus A2 B2. That's already been shown to be this particular expression here. So that's A1 S2 minus S1 B2. That expression now is going to be inside S because both of these things belong to S. Specifically because S is now an ideal. But ideals are also subrings, and consequently A1 S2 minus S1 B2 belongs to S because S is a subring as well. It's important to remember S is an ideal will imply that S is a subring, even though it does not go back the other way. And so what we have shown is we've shown that if S is an ideal and A1 plus S is equal to A2 plus S, and B1 plus S is equal to B2 plus S, then we've actually shown that A1 B1 plus S is equal to A2 B2 plus S. And what that means is that as long as we have S is an ideal, our coset multiplication is going to work. In other words, what we have done in this video is we have proved the following lemma. So we have now proved this important lemma. Let me actually write it properly as a lemma. Let R be any ring. Let S be an ideal of R. Then the coset multiplication is well defined on the quotient structure R mod S. In other words, we have a chance that R mod S might be a ring. We'll investigate that